Okay, hello class. Back to our last part in this chapter. Okay, today we're gonna proceed to the two-phase system. Firstly, we have learned about the residual properties. Okay, the residual properties is based on the actual minus the properties of the in the ideal gas. Okay, the residual properties can be determined by using the equation of state. Usually we're gonna use the generalized correlation by identify the range of the pressure. If the pressure given in the problem is lower or less than 15 bar, we're gonna use the virial coefficient to determine the desired properties. Otherwise, if the pressure is higher than 15 bar, so we're gonna choose a Lee Kessler based on the or referring to our reference table from the textbook. Okay, in this today's topic, we're gonna proceed to learn about the two-phase system. First, we cover the thermodynamic properties, which you should able to define the properties such as pressure, volume, molar volume, enthalpy, and as entropy of a substance on a single plot. And we will learn about the Clausius-Clapeyron equation and what is the concept used in this equation to relate with the to the two-phase system, and also how can we apply this equation in solving the problem. Okay, back to the phase diagram that we have learned previously. Okay, this diagram shows the pressure versus temperature. We can see the difference of the region. We have the solid, liquid, and also the vapor region. It based on the range of temperature and pressure. Okay, the phase change at given temperature basically is based on the extensive thermodynamic property, such as the molar or specific properties such as molar volume, enthalpy, entropy, and internal energy vary significantly. We can see that the phase change at the given temperature, we have a significant value of these extensive properties. Okay, during the phase change, the temperature and pressure is a constant. Those all phases we have the same, gonna have the same temperature and pressure. Okay, similarly, when we consider on the Gibbs energy of a pure substance also does not change during the phase transition, such as during the melting process, vaporization, or sublimation. Thus, the delta G equal to 0 at constant temperature and pressure, or it turns to delta G alpha here, maybe the phase 1, or this is our second phase, gonna be equivalent or constant. So we can get the delta G alpha at maybe phase 1, and delta will equal to delta G beta at second or another phase. Okay, this diagram for the pressure versus molar volume for the pure substance is shown the region of the between solid. We have the liquid, vapor, and other the down we have the liquid vapor region. Okay, the right diagram shows the liquid vapor and vapor region with isotope. We can see that the dotted line here is the temperature, and we have the critical temperature at point C here. However, as increasing or the temperature higher than critical temperature, we can have the superheated region. All this already explained to you previously. Okay, to test your understanding, what is the value of P liquid saturation and P vapor or pressure saturation vapor at 20 degrees Celsius? Okay, what are the value of enthalpy for that range of the pressure. Okay, example here, we can see the diagram is for the pressure versus enthalpy. Okay, the blue color here is the value for the information about the temperature. And we have the entropy represented by the red line. And then we have the molar volume and also its quality here. Okay, let's take a look to the question. Identify the value at 20 degree Celsius. So you may take a look on this, on the blue line here. So at 20 degree Celsius here, okay, maybe I can change. At 20 degree Celsius here, what is the pressure for? Okay, identify the value for pressure or liquid for saturated liquid and vapor. So from this, we can have the same. Okay, if we have 20 here, we can have the same pressure, right? So we have this. Okay, this is line for the pressure. So this is the value at 20 degrees Celsius. Okay, what are the value for enthalpy for both pressure? Okay, for the saturated liquid, okay, we have this is the saturation line here. Okay, this is our saturation line. So for the left side here is the liquid. So at the first line here or touch this line, at this pressure, so we can have this enthalpy or the value of enthalpy for the V saturation for the liquid. And then we can drag this line until we can have here. Okay, this is our next line. So the enthalpy here, or this is enthalpy or saturation enthalpy at the vapor. So you can see that the value is at constant temperature and pressure has a significant value of enthalpy along or at given temperature and pressure. So before we proceed to the Clausius-Clapeyron equation, you should understand the basic concept of the saturation. Okay, the liquid does not have any fixed boiling point or saturation point. Example, for water at 1 bar, it has the saturation temperature is 100 degrees Celsius. But if we increase at 2 bar, the saturation temperature will be increased a bit. Same goes to 5 bar and so on. Okay, the other such as ammonia. At 1 bar, the saturation temperature is minus 33 degrees Celsius. And we increase the temperature, the pressure, the temperature tends to be positive or increase as increasing the pressure. Okay, this specific volume of vapor is very high compared to the corresponding liquid. Okay, back to the previous example here. If we have the pressure versus a volume, so the specific volume for the gas is much higher compared than the liquid. So we have G higher than VL. Okay, the critical pressure in which liquid does not have two distinct phases anymore. Okay, we have this diagram, example P versus V, and this is our critical pressure or at certain critical temperature. So if we have this line is for the temperature, so if we have P critical or at critical pressure, critical temperature or pressure here, there is no more two phase because it above that or not under the dome. So this is our two phase region, liquid vapor or solid vapor. Okay, these are the player or introduced or the Clausius and Clapeyron equation from the German and French. Okay, the Clausius and Clapeyron equation example. Okay, this is example for water. Okay, the basic idea that the Clausius-Clapeyron equation provides a mathematical relation that describes any equilibrium state of water as function of temperature and pressure. Okay, from the previous data given, we have as we increase pressure, the temperature will be increased or it can. So we have that pressure and temperature, so it will exponential increase. So from the pressure versus volume here or specific volume here, the two-phase system can be observed under the dome. Here we have liquid and vapor. So it converts to the P versus temperature. Okay, we can see that two phases can be observed here from the maybe from the liquid to vapor that occur the vaporization process. Or we have also from the vapor to liquid or known as the condensation process. Okay, by consider a pure liquid in equilibrium with its vapor in a piston, a cylinder device at temperature and its corresponding P as a P saturation. Okay, what is saturation pressure? Okay, let's take a look. In a closed container, we have a water here or liquid water, and the temperature or initial temperature may be at 25 or room temperature, and then we heat up here, we supply heat, the temperature will be increased or exponential increase. And then from the vapor or the liquid that contain only liquid, when we heat up the container, it will have a vapor or tend to have the molecule inside or the molecule of water will be interact or will move rapidly, and then the molecule will tend to move from this liquid to gas or gas phase here to be a vapor. And then at the same time, when we increase or at height with introduction of the pressure or because of the pressure inside this container, the liquid or the vapor will turn back to the liquid and it will occur simultaneously. So if we have the molecule return or back to return to become a gas, and then the gas will be try to have this turn back or return back to the liquid. So it will have the rate here or equilibrium rate. So the pressure here, since we have the equilibrium rate here, the pressure known as the saturation pressure or as the third temperature at equilibrium at given temperature and pressure. So back to the Gibbs energy, correlation of the Gibbs energy, we have dG equal to VdP minus SdT. Since at equilibrium phase, the delta G or dG at alpha will be equal to delta G at beta. So alpha and beta is the different phases for the pure substance, which coexisting at equilibrium. So when we turn or we rewrite back to based on the VdP minus SdT, we gonna have V alpha dP saturation minus S alpha dt equal to V beta dP saturation minus S beta dt. So when we arrange this, we can have this equation. So you can see here we have dP saturation over dt equal to S beta minus S alpha equals to delta S. So from the Maxwell equation relation, that entropy is the categorized under the unmeasurable property. So we will try to have another correlation. Okay, back to here. We have the dH equal to TdS plus VdP. So this is the delta S alpha beta here. So we can, instead of using entropy, we can have the delta H, or delta H known as latent heat of phase transition. And then finally, after we can get, instead of having the entropy, we can have the latent heat here. Or for the alpha beta, or if we have liquid vapor here, it turns to delta H, liquid vapor. And we can rearrange it until we can have ln P saturation by performing the integration equal to minus delta H liquid vapor divided by gas constant universal times 1 over T plus C. So it equivalent to Y equal to Ms plus C for the linear equation. So we can have this or define this value using this linear equation. Okay, by assuming that the vapor phase is ideal gas and the molar volume of liquid is negligible compared with the molar volume of vapor. So instead of having delta V, liquid vapor, we can consider as V molar volume for vapor only. So this equal to RT over P saturation. The Clausius-Clapeyron equation only valid for two-phase system which involve the vapor phase, because we consider that delta V liquid vapor is equal to V vapor, or specific volume for the vapor phase. Okay, this is how we rearrange. So we can have the slope equal to delta HLV over or divided by R, or universal gas constant. Clausius-Clapeyron equation relates a latent heat of vaporization directly to vapor pressure curve, because we have a delta or ln P saturation here, or other words, the delta HLV directly proportional to the slope. That's why after we rearrange for the linear equation based on YMS plus C. However, the delta HLV will be decreased monotonically with increasing of temperature from the triple point to the critical point, where delta HLV equal to 0. Okay, this is another how can we rearrange or shows the diagram from the relation between the vapor pressure to the temperature, or increase exponentially, and then we can have a linear, or convert into the linear equation. So we can determine the delta H, or at vaporization, which ln P is the natural logarithm of this vapor pressure, and the delta H vaporization is the heat of vaporization, and R is our universal gas constant, which is the 8.31 joule a kilo Kelvin mole per mole, and the T here is the absolute temperature, and C is the constant, which is not related to the heat capacity. Okay, in summary here, the Clausius-Clapeyron equation, okay, by plotting the ln saturation pressure versus 1 over T yield a straight line. Okay, refer to this, and then this is the Ross estimation for vapor pressure from triple point to critical point. So the range of the temperature is valid from the triple point to critical point only. Okay, it's known, this equation known as Antoine equation, which is more satisfactory for general use. For each substance, it has own critical or Antoine equation, with A, B, and C are the constant for each substance. You may refer this value from table B2 from your reference table which are valid for the temperature range and should not be used outside the range. Okay, for each substance, it already mentioned what is the range for the temperature that refer to the value of the constant for each substance. The Wagner equation represents vapor pressure expressed in reduced vapor pressure. So it also can be expressed based on the reduced pressure as function of reduced temperature, where A, B, and C or D, if we have the values, it can be expressed by using this expression. Okay, this is how you can extract the information or the value A, B, and C depending on the substance, which it mentioned already the range of temperature for each substance. So you may refer to the range of the temperature, and then you can insert the value of constant to your Antoine equation. Okay, this is based on the degree Celsius unit. Okay, what is the latent heat vaporization? Okay, the latent heat is the required energy to exchange or to change the phases. Example, if we have the latent heat vaporization, so the phase change from the liquid to vapor, or latent heat of melting fusion is from the solid to the liquid, and latent heat of sublimation from the solid to vapor. So all of these at constant temperature and pressure. So we can use the Clapeyron equation to determine the latent heat. Okay, when no suitable data available, following approximation can be used. If we don't have the available data, we can refer to the Thornton rule, approximating heat of vaporization at normal boiling point Tn at P equal to 1 atmospheric. So we can use this Thornton rule. Okay, other equation is radial equation. Okay, it based on the critical pressure at a normal boiling point. And the second is Watson equation, approximating heat of vaporization at any temperature based on a known heat vaporization at certain temperature. So we can also determine the latent heat by using the reduced temperature based on the Watson equation. Both Thornton's rule and Watson equation only applicable if no suitable data available. Okay, let's refer to the example here. We have the data of temperature and saturation pressure. Okay, based on the data, plot a suitable diagram that can be used to estimate the latent heat of vaporization for carbon tetrachloride. So we can plot the data. We know that for the Clausius-Clapeyron equation, the ln delta or ln P saturation 1 over versus 1 over T. So we have temperature and saturation pressure. So by convert the unit first, we can have 1 over T and ln P saturation here. And then once we plot the graph, we can have the linear line here. So this is our equation based on y equal to mx plus c. So y here is, we have ln P saturation, and this is our 1 over T. So from this loop, we can define our latent heat or delta HLV. Okay, this is the way you determine the delta HV from the data given. Okay, next example, vapor pressure of benzene is given by the following. Okay, this is known as Antoine equation. Antoine equation. We have ln P equal to, okay, this is A, and this is B, and this is C. So the equation and all the constant are given here. So the question is estimate the entropy change for the vaporization process of the benzene at 50 degrees Celsius by using a Clapeyron equation. Okay, the Clapeyron equation, dP over dt equal to delta H, or latent heat vaporization over T, delta V. This is the given equation from the Clapeyron equation. We have T V L V for the approximation of the value of. So we have this dP. So how can we start is to determine the P saturation first, because we have the delta P saturation, delta T also given. So we need to determine the delta V here, because we can correlate the delta V to the entropy. So we start, okay, this is the Antoine equation, and then T given is, this is our T at 50 degrees Celsius. And we can, by inserting this value, we can determine our pressure or saturation pressure. Okay, delta V is based on the V at a vapor minus specific volume at a liquid. So for the liquid, we can determine it based on the Racket equation. And then for the V saturation, we can determine it based on the critical volume and critical for the compressibility factor. This value you may refer to the table. Okay, by referring to the table B1, the substance is benzene. Okay, list all the properties here. We can get the volume for the critical, specific volume, critical for the compressibility factor, critical pressure, temperature, and eccentric factor. So we can determine the reduced temperature and pressure here. Okay, by inserting this, we can get the saturation volume here, or saturation of the specific volume. V saturation, also known as the liquid, or V volume at a liquid. Okay, for the volume, specific volume for the vapor here, we can use Spitzer, or if you can see here, this is based on the Spitzer here. Okay, because we have the pressure here at, okay, from the calculation, pressure is 0.36, which is the P here is 0.36 bar. We have a lower than 15 bar. So we can use the based on the virial equation. So no need to refer to the Lee-Kessler. If we use the Lee-Kessler, we may refer to the reference table. So using a virial equation here, okay, you may use this equation or based on the Spitzer here. Okay, first you need to determine based on the PV equal to ZRT. So V equal to ZRT over P. So we need to define the Z, P here, all the information. Finally, you can insert to obtain the V for the volume. We have this R here, and then this is this, all the B naught. Okay, you can use this equation. So we have RT, T is given, P is at 0.36 that we determined previously, and then we can have V naught, eccentric factor for the benzene, B1, PR, TR. So basically, we can have the value of V. And then the delta S here is equal to delta H over T. So you can use or determine this, okay, because we have this delta V here, or delta VLV here, and then finally we can determine our delta S. Okay, this is how we solve this problem given here. Next, okay, so we already end our part for this chapter. So basically, we already in this part we already cover how can we define the other properties based on the diagram by using the thermodynamic properties diagram, such as the correlation between PV diagram or pH diagram, in order for us to determine other properties such as entropy or the enthalpy, etc. And then we also cover the Clausius-Clapeyron equation. Okay, this equation is to determine the latent heat, which the latent heat is determined based on the linear equation by rearrange of this correlation between the vapor pressure and temperature. And the last is we also apply or learn how to apply the equation to determine other desired thermodynamic properties, such as here we determine the entropy. So for the next topic, we will learn about the vapor liquid equilibrium. This is our new chapter. I hope that you able to cover or understand all the parts in chapter 3. Okay, by the end of this, I'll meet you in the next topic. Okay, thank you. Bye.